So we are here for lecture 8 on the course Proof Complexity as a Computational Lens. So today we are moving on to algebraic proof systems, mostly, except that old habits die hard. So towards the end of the lecture, we'll end up talking about resolution anyway, but this is mostly just to prepare us for what will come, because there's an interesting parallel between resolution and algebraic proof systems that we will explore. So let's fix a field, let's fix a set of variables. Usually when I just write x with an arrow or just an x, that means a set or an ordered set of n variables. And we're going to have a bunch of polynomials, p1 up to pm. So it will tend to be the case, unless stated otherwise, that n will be the number of variables and m will be the number of polynomials, or something somewhat related to the number of variables or polynomials. So we're getting a bunch of polynomials. And suppose we're also insisting on Boolean solutions, so 0-1 valued solutions. So we'll throw in so-called Boolean axioms, xj squared minus xj for all variables j. And now we're interested in whether there is a common 0-1 solution to all of these polynomials that make all of them vanish. And what Nullstellensatz tells us is that there is no common 0-1 valued solution. If and only if there are polynomials qi and rj such that I can write down, summing from I goes from 1 to m, qi pi plus j goes from 1 to n, rj xj squared minus xj, and then I just sum everything up, and when the dust settles, I just get syntactically 1, which is the multiplicative identity in whatever field we are. We don't care too much about what field we were today. I mean, it could be the rationals, the reals, the complex numbers, could be your favorite final field, GF2. We don't really need to talk about it too much. So this we can refer to as a Nullstellensatz certificate of unsatisfiability. And just to say that it's clearly the case that if I can write down an expression like this, you should agree that there's no 0-1 valued solution, because you plugged in a 0-1 valued solution and the left-hand side would obviously vanish. Right-hand side does not vanish. The other direction is not obvious, requires an argument that I'm going to skip. I'm just going to say that we do need the Boolean axioms for this goal.
There's a question in the chat. Hilbert's Nullstellensatz is only true for algebraically closed fields.
Exactly.
Right?
That's why I need these axioms. So it's by a slight extension of Hilbert's Nullstellensatz, and that's what I'm saying is true, provided that we insist on 0-1 solutions, and that requires an argument. There's so much we could talk about today. I'm going to skip this argument. Okay? But it's absolutely true. So now we're actually going to care about arbitrary polynomials. But of course, we also care about CNF formulas. So here is a clause over positive variables, positive literals x, or negative and negative literals, not y. I want to view this, like, how would I translate this if I want to do Nullstellensatz? I have to write this as a polynomial. And now I'm going to be slightly inconsistent with what I did in the first lecture, I think. I'm going to do this. I'm going to write the polynomial p representing the clause c as just taking the product of all the positive literals. And then for all the negative literals, I'm going to take 1 minus 1. So we're actually going to think of 0 as true and 1 as false for a couple of lectures going forward, except we're going to be a little bit schizophrenic sometimes. But the point is, when you're in an algebraic setting, something being true, we saw it already here. What does it mean to satisfy things? Well, things that are satisfied, they vanish. They go to zero. So therefore, you could build polynomial calculus by just saying, okay, I'll think of 1 as being true and 0 as being false, because that's what I'm used to as a computer scientist. But then you would have to distinguish between an x is true, and then you would have a unit clause that represent x, and it would look kind of different. Then it's a little bit weird. So for at least for today's lecture and next lecture, we'll just think of 0 as vanishing as being true, and 1 as being false. I should know that we'll be slightly schizophrenic about this going forward, and that is because, well, the literature is schizophrenic. We'll do whatever, we'll be opportunistic and do whatever suits us. Okay, so one thing that I'll also use with, well, so I'll use two things about this Nullstellensatz proof system. So I can then, what I said, I'm going to go over this very quickly because basically we're not going to talk much about Nullstellensatz, but clearly with this translation now, Nullstellensatz is a proof system for any polynomials, in particular for CNF formulas. Namely, if I have an unsatisfiable CNF formula, I translate it in this way, and I get a bunch of polynomials. I write down a certificate like this. That's one proof of unsatisfiability. I could also imagine deriving other things, and in fact, we have that. So let me write down just for the record that Nullstellensatz is sound and implicationally complete. What does this mean? This means that if I have a bunch of polynomials and then also let's throw in the Boolean axioms, again, they are important. And suppose they imply a polynomial p. What does this mean in this setting? Any 0, 1 valued assignment that makes all of these polynomials vanish must make p vanish. Okay. Suppose that this holds. This is true if and only if there exists qi and rj, so that I can write p on this form. Again, note that this is in general not true. I'm heavily using Boolean axioms here. Okay, this requires a proof that I'm not going to give you. Are we happy so far, modulo the fact that I'm refusing to give you proofs? One piece of terminology, a monomial, and this is also another aspect where the literature is a little bit schizophrenic. For me, a monomial is going to be just a product, a polynomial that is a single product of variables raised to some powers. Very soon, these powers are all going to be 1. We're not quite there yet, but I'm just warning you. Okay. Now, a term for me is going to be alpha times m for some field element alpha. So here, the monomial just picks out the variable. The term also says, oh, there's a field constant in front. I care about what that constant is. The literature is not consistent here. Sometimes people swap and use a term for this and a monomial for this. You just have to be, whenever it matters, you have to be clear what you want to say. We are going to represent our polynomials as linear combinations of monomials, meaning as sums of terms. If you give me a polynomial, I'm not going to talk to you unless you write it down as a sum of terms over distinct monomials. That's my polynomial representation. And then I can write the size of a polynomial as the number of monomials in it. Okay. This is not the only imaginable measure. I mean, you could imagine, what if I have a great, super nice, clever algebraic circuit computing this polynomial? Couldn't I give you the circuit instead? And no, not to me. Maybe, you know, if you talk to Srikant Srinivasan, for instance, he would be willing to discuss with you, but I won't. There are two reasons for this. One is that we have this slight computational perspective on things, and then this is the representation that makes most computational sense. Another slightly embarrassing problem is that, well, if you insist on more intelligent representations of your polynomials, then I won't be able to prove any lower bounds for you. As I said, then you actually get another proof system that basically we're getting a little bit ahead of ourselves. We won't talk about it. You get things like the ideal proof system, and that is up in the realm where sadly our tools really do not work. So, but for Nullstellensatz proofs, I can now define the size of a proof, and that will just be basically summing up all of the sizes of these QIs, PIs, and all of the sizes of the Rj squared minus Rj's times sorry, I didn't mean that. What did I mean? I mean Rj times x j squared minus xj, I guess what I meant, and then the size of that. Okay, that's the size of a Nullstellensatz proof. And then I'm also going to measure the degree, and that is just the largest total degree of anything you see in here. Okay, and then just as we did for resolution, now I can consider all possible Nullstellensatz refutation, and I can take the minimum, and that will define the size in Nullstellensatz of refuting a set of polynomials and the degree. Okay, and these measures are not necessarily minimized for the same refutation, obviously. And just for notational consistency, I will write something like, you know, the size in Nullstellensatz of refuting the set of polynomials B. I'll use, like, for any proof system, any measure we come up with, I'm usually going to write, like, you know, here's the measure, the size, here's the proof system, here apparently Nullstellensatz of refuting. And then, you know, what does bottom mean? Well, now for us, bottom is 1. Before it was the empty clause. You realize, by the way, that we're at least being consistent, because if I take the empty clause and translate it to a polynomial, I'm going to get 1. But in that sense, it parses.
We don't care about coefficients. Like if the coefficient is very large, we don't care.
No, you get them for free. I'm feeling generous today. There is, you can, if you want to be super precise, people have studied bit size. Firstly, that only matters over fields like the reals or the, you know, rationals or things like this. Mostly, I guess I told you not to worry about the field, but I lied a little bit. You know, my favorite field is finite. So I don't, and then clearly I don't care about the coefficient, but it's a good question. There are papers carrying out about this, and then you can talk about bit size. We're not going to talk about it at all, I think, in this course, unless you convince me otherwise. This is what I wanted to tell you about Nullstellensatz. Now we're immediately going to move on to something else. We're not going to, there's a literature on Nullstellensatz, there are lots of nice things. Maybe later in the course we'll talk about one very concrete result, but basically I'm just going to move on to something more interesting. So any questions on Nullstellensatz, you should ask them now or remain forever silent. This makes sense? Okay, why am I not happy with Nullstellensatz? I'm not happy with Nullstellensatz because, because this is not a very efficient way of writing down my proof. Somehow in one shot, I have to write down everything. And what you're really doing when you're writing down a derivation of a polynomial, what does it mean that a polynomial is implied only if it is this kind of, you know, can be written at this kind of polynomial linear combination? Well, it means that the polynomial lies in the ideal. Okay, so what's an ideal? So suppose that R is a commutative ring. Then an ideal in R is a subset such that the following two things hold. So firstly, it should be a subring. So if P and Q are in I, then P plus Q are in I. So an ideal is closed under addition. If it's a subring, it should also be closed under multiplication. But an ideal is more closed than that. So for an ideal is like for any R in the ring, and for any P, R times P lies in the ideal. So the ideal is sort of absorbing, if you wish, under multiplication. And now, once you fix your finite field and look at polynomials, we're going to basically what Nullstellensatz is doing, it's arguing about the polynomial ring. And it's arguing about this is nothing else than saying that P lies in the ideal generated by these polynomials. And we'll use the notation an ideal generated by a bunch of polynomials fancy style P is just with angle brackets. Okay, so this is the ideal. And usually whenever I'm a little bit hazy about this, let me throw in the Boolean axioms in fancy style P just because then I have to type less. Then basically what we're saying is that a Nullstellensatz refutation just shows that one lies in the ideal generated by all these polynomials. That's exactly what Nullstellensatz does. But the question is like, why do I have to show this to you in one shot? Why can't I just use these rules to sort of build a step-by-step derivation showing maybe more efficiently how one lies in the ideal? Okay, that's polynomial calculus. Let me write down what polynomial calculus is. A polynomial calculus derivation of lowercase p from a such fancy style P, where again, let me throw in the Boolean axioms just to be on the safe side. It's a sequence of polynomials, P1 up to PL, such that, well, it should be a derivation of P, so the last polynomial PL is P, and then for all PI in the sequence, pi, it holds that either PI is in P, or, and now I'm actually going to be a little bit picky. Let me say that either it's in PI minus the Boolean axioms, and then I'm going to say it's, I don't know, let me say it's an input axiom. And if PI happens to be xj squared minus xj, I'll call it a Boolean axiom. I want to distinguish these. And that's one reason for it is that we'll get rid of them soon. And otherwise, PI is derived from previous polynomials, from some pj, or maybe some pk for j and k both less than I. And we have two rules. We have linear combination that says that if I have q and r, then I can take alpha q plus beta r, the linear combination where alpha and beta are constants in my field. This linear combination. And then I also have another rule that is multiplication. So if I have any polynomial q, then I can take m times q. This is multiplication by a monomial. Multiplication. And one way to think about resolution, as we argued before, was we thought in our heads, okay, suppose I have a satisfying assignment to my original input clauses. Let me derive new clauses that are also guaranteed to be satisfied. The way you can think about this, if you like, is suppose I have a satisfying assignment, meaning an assignment for which all the PIs in P vanish, then these rules clearly allow me to derive new polynomials that also vanish, right? If P and Q vanish, then any linear combination vanish. If Q is already 0, then multiplying it by something doesn't change that. Make sense? And now a polynomial calculus refutation. That's just a derivation of 1, as before. And now we have three measures. We have the size, which is defined as before. I just take the size of, sum up the sizes of all the polynomials that I see. We have length, which in this case is just the number of steps. And then I have these. And then I can also define the size, the length, and the degree of refuting a set of polynomials by taking minimum. And then I'll use the same kind of notation as here, except then the subscript will be PC instead of NS. Yes?
Is the degree the maximum degree or the sum of degrees?
The maximum degree. Maximum degree. So I go over, I look at, so the degree of a monomial is just, sum all the powers up, right? Except they're all going to be 1 soon. And then the degree of a polynomial is take the max over all the monomials in its representation. And the degree of derivation is the max of all the polynomials. Yes. Make sense?
So could you have, like, you already count the degrees of the PIs, right? But maybe in a linear combination, you temporarily have
some larger thing that somehow cancels. Yeah, no, let me just count the degree of these cases.
Okay.
Okay, so this is what we want to talk about. Okay, but now there's one, okay, there are two slightly annoying problems now, two technicalities that I want to get out of the way. One is that I kept talking about monomials and general degrees. We want to get all degrees down to 1. But let's talk about something that is even more annoying. Consider the following clause. C is the OR from I goes from 1 to n of not xi. Let's translate it to a polynomial. PC. Well, that's just going to be, that's not hard to translate. That's 1 minus xi. Right? Which is then going to be, we're going to sum over all subsets of n minus 1 to the size of the subset product over I in the subset xi. Okay? Which you realize now this is an exponentially large. On the one hand, this is great. We're usually shooting for exponential lower bounds, and here the exponential lower bound is right there. We haven't even done any work. That's fantastic. Except that we somehow want to, we want the input to be a polynomial size. So this is a problem with algebraic proof systems, and there are two ways of dealing with this. One that I know, or maybe more, one thing would be to say, well, if you're going to work on CNF formulas, then make sure that they are of constant width. And we know how to do this. Suppose that I have a general polynomial, general clause with n literals, then I can just throw in a bunch of auxiliary variables, AI, and let me write down the following set of clauses. A0, the unit clause A0 false, A1 or X1 or A1 false, A1 or X2 or A2 false. Keep going. Let's see if I can get the indices right. AN minus 1 or XN or AN false. And then saying that no, AN has to be true. it's kind of clear. Okay, except I switched from x's from L's to x's, so let me switch back. These are the LIs, same one as over there. It's kind of clear. Morally speaking, these are equivalent, right? I mean, any satisfying assignment here gives a satisfying assignment here and vice versa. Of course, formally speaking, they're not equivalent because they're over distinct variable sets. But, I mean, for some notion of equivalent, it's kind of... So we could just say that, you know, whenever you run into something like this, then do the... There's even a standard notation for this that I might use later. If this is the clause C, then it's a fairly common notation to say that this is the clause at tilde C. Just the 3CNF version. Okay, so we could do this and just say that we're going to work in polynomial terms. But there's also another way. This is like facing the problem and doing something with the problem. We could also just, refuse to face the problem and remove it. And that's actually mostly what we're going to do. So we could just say that I'm going to have more variables. I'm going to have variables xj, but let me also introduce xj bar. So note now that I have two n distinct variables. Of course, you might think that they look similar, but they're formally completely distinct algebraic variables. They just live in the field left. Okay? Except that I'm going to have Boolean axioms over all of these, but I'm also going to add complementarity axioms xj plus xj bar minus 1. Let me call this complementarity axiom. Complementarity or negation axiom. So whenever you have a polynomial encoding or you want to translate the CNF, I just, throw in, I do the CNF translation, and then I throw in the Boolean axioms, and then I throw in the complementarity axioms. And now I'll translate C to just a monomial, right? So for the positive literals, I just take X, and for the negative literals, I just take Y bar. And now there's no exclusion. Problem solved. The rest of polynomial calculus is just as before. The definition of what it means to be a refutation is just as before. And this is sometimes, or it's known in the literature as polynomial calculus resolution. That's a lot of typing, so it's more convenient to say PCR. And that is, I think, what we are mostly. You should think of when we're going to work with polynomial calculus. You should think of PCR. Like in particular, all the lower bounds we will prove will apply for PCR. Okay, and this is what we want to talk about. So now I want to tell you quickly about some things about polynomial calculus. Maybe a little bit about Nullstellensatz also, a little bit about PCR. And then hopefully at some point we're going to get to theorems that we want to state and prove. But okay, so do that before we get to. So now we have like 3 proof systems on the board. We have Nullstellensatz, we have polynomial calculus, we have polynomial calculus resolution. Sometimes you can also refer to it. These variables are sometimes referred to as dual variables. So you could say that this is polynomial calculus with dual variables, except that I think PCR is what people will usually write when they write papers. So questions about these definitions? Or are they more or less clear? Okay, let's state some obvious facts and some less obvious facts. Well, clearly PCR is at least as strong a proof system as polynomial calculus. I mean, in some sense, if I give you a set of polynomials that are only over positive variables so that I can talk about them in both encodings, or otherwise you can sort of define a translation if you like, then basically polynomial calculus is just PCR without using the dual variables. It's an interesting question whether they're different in power. And the answer is yes. Although surprisingly, so we actually wrote this down a few years ago. This is the Zemde, Lauria, Dmitry Sokolov, and myself. It appears not to have been known before then, but you can actually, like the possibility of using dual variables, there are constant degree polynomials, constant width CNFs, for which if you're able to use the dual variables, then this increases your reasoning power exponentially. It's not so hard to see, and I'm not gonna prove it, but when it comes to degree, we don't care. Right, and this is because x bar of 1 minus x, I mean, sure, things explode, but the degree doesn't change.
Are those CNFs easy for resolution, the ones from Deers and the Nordström?
Yeah. I think you can. I think the one we did are probably. I don't know if you can tweak them so that you can make them both easy and hard for resolution. I don't have that in cache. Sorry. Good question. By the way, I'm not going to talk about that either, but you realize that this trick with dual variables, like why can't you do it for Nullstellensatz? And of course you can. And the question is, what should you call this proof system? And this is like, you could call it Nullstellensatz resolution, I guess, but that becomes kind of a little bit weird, maybe. But whatever you call it, Nullstellensatz with dual variables in the same paper, for pretty much, I think you also did it for Shirley, Adams, and SOS. I mean, for any of these, you can introduce dual variables and it increases the reasoning power exponentially. Okay, degree is the same. Polynomial calculus, just to say one thing, already without dual variables, polynomial calculus is much stronger than Nullstellensatz. And I'm not going to prove this either, but it sort of motivates why we want to talk about polynomial calculus. In terms of size, we can get polynomial in n. I'm sometimes going to use this notation poly n. That just means that n raised to some constant versus exponential in some n to the delta. For degree, there's also a very strong separation. You can have constant polynomial calculus degree and n over log n for Nullstellensatz, where n is the number of variables and also the size of the whole input object. So Nullstellensatz is much stronger. We also have that polynomial calculus resolution, and this is maybe why it's called this, it efficiently simulates resolution. What this means is that suppose that I have a resolution refutation of some formula f. Okay, then I can find a PCR refutation of f. And note that here what I mean is, well, the translation of f into polynomials. Such that the size of the PCR refutation is linear in the length of the resolution refutation, and the degree of the PCR refutation is actually upper bounded by the width of the resolution refutation. How do you do this? Well, basically, you just go over the resolution refutation line by line, and you show how in PCR you just simulate the resolution step. I'm not going to do this. This is a nice exercise. Not hard. Already polynomial calculus without dual variables can be exponentially stronger with respect to size than resolution. And in fact, the formulas we've talked about so far are examples of this. So if you take Sapien formulas, and if you say, well, I'm going to do polynomial calculus over GF2, then parity reasoning in GF2 comes for free, right? You're just adding up things in GF2 is parity reasoning. So you're just going to sum up all the constraints and deduce 0 is not equal to 1. Perhaps a little bit more interestingly and independent of the field, if you remember, we hand-waved very quickly but very vigorously towards the end of last lecture that using the machinery we built there, you could actually get resolution, exponential resolution lower bounds for the onto functional pigeonhole principle, which is also known as perfect matching, perfect bipartite matching. These are formulas that are exponentially hard, saying that you're telling a resolution that I have a bipartite graph, n plus 1 vertices on the left, n vertices on the right. There's perfect matching. Resolution takes an exponential time to figure out that this is not the case. Polynomial calculus will just sum up the number of vertices on the left, the number of vertices on the right. Now, if you're in a finite field, you have a little bit of a problem because you cannot sum. You can only sum modulo the field characteristic. But even modulo the field characteristic, n plus 1 and n are distinct numbers. But if it's a perfect matching, then they have to be the same number. Yeah, and then you just have to like work out the details that polynomial calculus can do it. So these are both easy for polynomial calculus, hard for resolution. So this tells us that polynomial calculus is an exponentially stronger proof. So there's a difference. There are also some similarities, and mostly we're going to explore similarities. So the paper that defined the original polynomial calculus by Clegg, Edmondson, and Palazzo, they showed that, well, suppose we have a set of polynomials, and again, I'm throwing in the Boolean axioms. Suppose they're refutable in degree D. Then the size of refuting these polynomials is actually n to the big O of D, where n is the number of variables. N is the number of variables. Okay. For resolution, this was like blind. We just counted the number of clauses. Here, you actually have to do some work. But it's an interesting parallel that means that, well, if I can do something in low degree, then I can also do it in small size. And where we're going, I'll take a few more minutes before we get there, but this raises the question about, well, what do we know about resolution since last time? Well, we know since last time that if we had, so two observations. In resolution, we know that actually, so width upper bounds gave us length upper bounds, but also strong enough width lower bounds gave us length lower bounds. Strong enough width lower bounds gave us length lower bounds. And if you think about it, width and degree are analogous measure, right? If you take a wide clause, if you take a clause and translate it to a polynomial, then the width of it turns into the degree. So it's natural to compare what holds for width and what holds for degree. So this raises the interesting question, you know, could you say something, do degree lower bounds tell us something about polynomial calculus size? And the spoiler alert is totally. Okay, but before we get there, let's get rid of these higher powers in our polynomials. So a multilinear monomial is something that just looks like, I just tell you which axioms are, which variables are there. Okay, so all variables appear with power 0 or 1. And now I claim that without loss of generality, morally speaking, anything we do in polynomial calculus is multilinear. Because as soon as you pick up a higher power, you just use the Boolean axioms to bring the powers down to 1. Now, this might take a few steps, right? I mean, you multiply something and things, maybe you get a lot of polynomials with powers of 2 and you have to remove them and it gets annoying. And also, like from an algebraic perspective, if you had an algorithm and you know you're doing Boolean stuff, then why don't you multilinearize right away? Yeah. And in fact, so we could define, so a multilinear monomial is something like this. A multilinear polynomial is a polynomial that only contains multilinear monomials. And we could define multiplication to just be multilinear. Let's just impose multilinearity. Or we could just say that we're not going to work in, before polynomial calculus, once we fix the field, we work in this ring, right? But now let's just agree that we're going to work in the quotient ring. So we mod out everything modulo xj squared minus xj. This is exactly the same effect as just removing all higher power. Okay. And in fact, this is what we're going to do from now on. And now it holds that all of our size. Okay, so how can this multilinearized polynomial calculus? How does this change things? It can only increase the power, right? But all the upper bounds I state will be for standard syntactic polynomial calculus without multilinearization for free. All our lower bounds will be with multilinearization. Except for one quite interesting fact, namely the following. Suppose that we have an unsatisfiable K CNF formula, F, and let me write out what F is. It's the conjunction of M clauses, C1 up to Cm. The length in PC, and maybe let me improvise and write MLPC just in this proposition for the length in multilinear polynomial calculus of refuting F is big O of K times F. So in particular, for any KCNF formula, you only need a quadratic number of steps to refute it, if we're counting length. Okay, so I'm not going to do the proof, but I can tell you the proof, and it's not hard. So by induction and a constant number of steps in every induction step, we just derive the polynomial Pj which is 1 minus the product of I goes from 1 to j, 1 minus the clause ci, so PCI, the representation of the clause as a polynomial. Let me actually be a little bit sloppy here and let me just identify them so that I'll write ci. Okay. Suppose that I can do this for every new and I knew. P1 obviously is, actually P1 is just the first clause. So then suppose inductively I can do this. In the end, we have PM, which is 1 minus product I goes from 1 to m, 1 minus ci. What can we say about this polynomial when we evaluate it over 0, 1 assignments? Always 1, right? Because for any truth value assignment, we're going to violate some clause. And then we're going to pick up a 1. And that means that this product is going to vanish. So we only pick up this one. So this is a polynomial that when evaluated over 0, 1 to the n is identically 1. It's not the identically 1 polynomial, but it evaluates the 1 everywhere. And now suppose I multilinearize this. Well, then we actually know, just by standard linear algebra, that for any Boolean function, any pseudo-Boolean function, any function that maps 0, 1 to the n to my field f, any such function has a unique representation as a multilinear polynomial. This is by basic linear algebra. And in particular, there's one multilinear polynomial that evaluates to 1 everywhere, namely this guy. And that means that the multilinear version of PM has to be identical to 1, just by linear algebra. What do we expect this refutation length to be if we don't have multilinearization for free? Well, then we expect it to be, probably exponential. Like we don't expect this to hold without multilinearization. But this kind of tells you that the only way you could prove length lower bounds for polynomial calculus is by somehow very cleverly arguing that you need an exponential number of multilinearization steps using Boolean axioms. And we just don't know how to do that. This is like, if you could do that, then that would be amazing. So we're going to focus on size, and also because size is, well, any algorithm you have is actually going to have to operate and write down these intermediate polynomials. So size also algorithmically makes sense.
Just to be clear, the CIs here are the polynomials, which means that when it's not satisfied, it's 1.
Sorry, say again?
The CIs here are not the CIs before. These are the polynomial translation of CI, which means unsatisfied is CI being evaluated to 1.
Yes,
Yeah,
I mean,
just
CI is
with confusion.
PCI.
Yeah,
So PCI is
yes.
this guy, yes. Or, well, 1 minus, I erased that already. Yeah, so again, we're using, that's why, again, so evaluating to 1 is being false, not satisfied. Evaluating to 0 is being true, because we're being algebraic to this. But yes, that's an important point. More questions about this? Okay, so then I don't know if you memorized what we did last time, but it turns out that long before Ben-Sasson and Wigderson, there was a theorem by Impagliazzo, Kudlak, and Skal, but not so long before, but in 1999, that says, again, I'm being, just to state this concisely, suppose that fancy style P is a set of polynomials, including the Boolean axioms. And I'm interested in what total degree I need to refute this. And it turns out, well, I probably have to mention all polynomials. So the degree of the input is probably a good, I can't really hope to do better than that. But then I say that, well, if you have a small refutation, even in PCR, in fact, even in multilinear PCR, then you can take the number of variables times the logarithm of the smallest possible PCR refutation and the square root of that, and that's going to give you an upper bound of degree. And now this should look familiar. This is exactly the same plug-in width here, plug-in length here. It's exactly the same statement as for resolution. Okay, so again, the degree is upper bounded, the refutation degree is upper bounded by the input degree plus big O of square root of number of variables times the logarithm of the length, the size of refuting the polynomial. And the really interesting thing, just as for resolution, is when we turn this around and we say that, well, then the size of refuting a set of polynomials, even in multilinear polynomial calculus with dual variables, will be exponential in the refutation degree minus the input degree squared divided by the number of variables n. Just as for resolution. And even more interestingly, like with hindsight, so this result came first. And then at the time, people wondered, like, is there anything similar for resolution? It's like, no, probably not. Yeah, and then Ben-Sasson and Wigderson came around and said, yeah, no, I mean, exactly the same result for resolution. And in fact, I'm not going to prove this because I claim that if you look at the proof we did, we only used that you can take derivations, you can hit them with restrictions, and then we use the fact that if I find a common literal, by setting it to the right value, I can make a clause go away. Okay, but polynomial calculus also is well behaved to restriction, and if I find a variable that is in a monomial, and if I set that variable to 0, then obviously the monomial vanishes. Okay, so you can take the proof we did, just line by line, substitute degree for width, resolution for PCR, and everything, and then just run exactly the same proof. So with hindsight, it's really the same theorem in some sense, but that was very much not obvious at the time. One thing we don't have, though, and I should have checked, but I realized now I didn't have the time to check, is you remember for resolution, we had a tree-like version. And I don't know if there's a tree-like version for PC. I mean, you can define tree-like polynomial calculus proof systems. And because the tree-like resolution proof, that actually used resolution in a more substantial way. So this I don't know. Okay.
So
Yes.
the original proof of this result used very different techniques then, or?
It's a good question. I think it depends on your point of view. I don't remember. I'm not sure if I remember actually. I mean, it was clearly different enough that when the Ben-Sasson and Wigderson paper appeared, it was like hailed as a new result. But if you read Ben-Sasson and Wigderson, I think it's maybe the way I don't know if I have a good answer. I think it's maybe the way we're doing the proofs now. But I mean, I don't have a good answer. I think it's like the math that was actually happening was probably the same, but you can sort of, if you phrase things in different ways, you can make it hard to see what's going on. Okay. So, what do I want to do? Where is this? I want to say a few more things and then we'll have a break real soon. Because now this brings us to the point where, okay, this tells us that just as proving with lower bounds for resolution is a very useful way in general of getting lower bounds for length / size. It turns out for polynomial calculus, proving degree lower bounds is a very useful way of getting polynomial calculus size lower bound. But there is a difference, and the difference is that for resolution, we can do lots of different things. I mean, we have this bottleneck counting, we have interpolation, we have this size-width relation, and you can like do different things. But I think it's fair to say that for polynomial calculus, except for these degree lower bounds, there's not much we can do. So we have a much smaller toolbox for polynomial calculus. So what we're going to talk about is mostly just, okay, how can we prove degree lower bound? And then we're going to say a prayer that our degree lower bounds will be strong enough if our degree lower bounds are asymptotically larger than square root the number of variables, log the number of variables, then we can hope to get something non-trivial out of this. If we fail to prove such degree lower bounds, then our options are very limited. There are some things you can do, and we'll see one other example where we cannot apply this, but it's pretty much almost all lower bounds for polynomial calculus size go via the size degree relation. So we're much more limited in that sense. And then the question arises, okay, how do we prove degree lower bounds? For resolution, proving with lower bounds is almost an industry now. Like it's an established technique. What we did last time is you can sort of basically just apply that recipe, you define the complexity measure, and then you sort of check, is this going to work out the way it usually does? Yes, it does. Okay, good, I have my lower bound. For polynomial calculus, proving degree lower bounds is a lot of pain. There are two things you can do. Okay, oops. So how can we prove degree lower bounds? Just for completeness, I want to mention that if method 1, if the characteristic of your field is not 2, so what's the characteristic of a field? That's you take the multiplicative identity 1, you just add it to itself. How many times do you have to add it until you hit 0? That's the characteristic of the field. If this is a positive number, we say the field has finite characteristic. If your field is R or Q or the complex number C, you realize that, well, you'll never hit 0, then we just say that the characteristic is 0. Okay. If your field has characteristic not 2, then you can sometimes do an affine transformation. You translate everything. You translate your whole proof, you translate your input polynomials, everything, so that 0, 1 will map to -1, 1. Okay. So if you before you thought of 0 as true and 1 as false, you're going to think of -1 as true and 1 as false. Okay, but in order for this affine transformation to work, it helps if -1 and 1 are different field elements, which is why you don't want characteristic 2. And then sometimes over in this representation, it's easier to prove degree lower bounds. And then you realize that, well, if you have a valid polynomial calculus derivation over here, and you just do an affine transformation, that doesn't change the degree. So any degree lower bound you get are valid in both settings. So then you translate that. But you can't do this in characteristic. Okay. The second approach is by arguing in terms of expansion of some kind of constraint variable incidence graph. Like you can now define, you can have polynomials on one side, variables on the other, and draw edges as before. And if this is an expander, you can say a prayer and hope that you get both. And this is what we're going to do. So we're going to use a paper by Alekhnovich and Razborov. except we're going to look at a generalization of this by Lund and Mikša and myself. And we're basically going to do what we did for resolution, but we'll try to lift it to polynomial calculus. And I'm going to spend the last few minutes before the break to just try to recap what we did, and then we should remind ourselves that whatever we did won't quite work, right? Because we built a closed variable incidence graph, and then we proved strong lower bounds for taking formulas and for onto functional pigeonhole principle. And we know that that's going to fail, right? Because those lower bounds are not true. So something will have to be different. Okay, so what did we do last time? So we had a CNF formula, fancy style F, and I wrote it as a partition of clause set, whereas a special mysterious clause set E, and then I had some other clause sets Fi. This was a partition. And then the variable set was fancy style V, and I wrote that as also a union of subsets of variables, except that now this was not necessarily a partition, but we looked at the max for all variables x of the number of variable sets vi in fancy style V, such that x was in vi. Looked at this set, we took the cardinality, and we call this the overlap. And this overlap was, we used the letter L, and we sort of said, well, this should be small, this should be constant. Actually, it's going to be like throughout this course, it's going to be 1 or 2. I think. No, wait, I take that back. Slightly lower, some small constant. Okay, and we built the. So somehow we were given a CNF formula, and we looked at it, and based on the structure of the formula, we grouped it into subsets of clauses and subsets of variables. Again, how did we do this for taking? Well, we said that taking formula is really talking about parity constraints. So let every parity constraint be like a set. A parity constraint contains many clauses, but somehow they're all together. So for taking, every parity constraint was an Fi, but all the edges were their own singleton variable sets. For the pigeonhole principle formula, we said, well, every pigeon should get a clause. That's somehow important. So that's an Fi. And then we said, well, we're really thinking about the different holes and how we occupy them. So we said for a fixed hole, let's look at all the variables indicating which pigeon goes to that hole. That's going to be a set Vi. Okay, so we somehow used our understanding of the formula to build some kind of structure like this. Once we committed to how to partition things, and for the pigeonhole principle, we said, oh, we only want to work with assignments that are partial matching. So all the other like hole axioms and functionality axioms, just we throw them into the set that we said that somehow all our assignments that we're going to argue about somehow just have to have this structural property that they're partial matchings. Okay. So once we did this, we built a graph, which I used the notation F fancy style V subscript E to keep track of this mysterious E. This was a bipartite graph with left vertex set all the Fi's, right vertex set all the Vj's, and the edges, we had an edge from an Fi to Vj if just the variables in Fi intersected Vj. So once I committed to this, that immediately generated a bipartite graph. And then we said, that a S delta E resolution expander was an S delta bipartite boundary expander. What does that mean? That means that for all subsets of vertices F prime in F that are not too large. So here, I'm not counting the total number of clauses here. I'm counting the number of clause sets. So if this set is not too large, and I look at all of the vertices on the right-hand side that have a unique neighbor in here. So they're neighbors of F prime, but they have a unique neighbor in F prime. Okay, that set, if F prime is not too large, should be delta times F prime. So if when building this graph, I got such a nice expander, and if on every edge Fivj satisfier wins the what we call the resolution edge game. Then I said this was a resolution expander. So what is the resolution edge game? Let's recall it. So it was two players. So the adversary started by playing an alpha that satisfies E, and precisely because 0 and 1 have slightly ambiguous meanings today, I'm writing top and bottom so that we don't need to worry what 0 and 1 means. So adversary plays some alpha. So we're playing this on the edge Fivj. Then the satisfier modifies alpha on the variable set Vj, resulting in some alpha prime. And we say that the satisfier wins if the new assignment satisfies the clause set Fi. But it also has to be a valid assignment, so it has to satisfy E. And this was the game we talked about last time. And then we proved, actually, we did an honest proof that if the CNF formula F, if there is a way of structuring it so that we get an S delta E resolution expander, then the width of refuting F was, in fact, strictly larger than delta S over 2 times the overlap. This we proved last time. And what do we want to do? What we want to talk about now, our goal with this lecture and the next, is to say the following. We're going to say that F fancy style VE, let's call it a polynomial calculus expander. If we build the graph in the same way, so we want it to be an S delta boundary expander. Boundary expander. But then we want satisfier to win the polynomial calculus edge game on every edge. Okay, so what is the polynomial calculus edge game? It is the game where you basically switch the order of place. Okay, so we know we're going to play on this edge. So satisfier starts by committing to a partial truth value assignment to VJ, such that all let me say it and then explain. All the clauses in E that are touched by rho are also satisfied. Okay. Remember that before we said that once the satisfier is done playing, we should satisfy all of E. Now this is only a partial assignment that probably doesn't even mention all of the E set. So it's not reasonable to ask that you satisfy all of it. I'm just saying that for some clauses in E, if you're not mentioning them at all, then clearly the adversary move should take care of satisfying E. So if you don't mention any variable at all for a clause in E, then that's fine, ignore it. But if you do assign some variables in E, then you have to satisfy that clause, because otherwise, obviously, the adversary will say, well, in my assignment, I satisfied that clause, but then you screwed it up when you flipped it. Okay? But the point is that satisfier has to go first. And now adversary makes the move precisely as before. Adversary plays an alpha such that alpha satisfies the filtering set. And now we get the same assignment as before. Let me use some improvised notation for this. So the satisfier wins if we take alpha, and let me say that we take alpha except that on the set Vj, we plug in what rho thinks. Okay, we're not going to use this notation going forward, but basically I take alpha except on Vj, I switch it to rho. Okay. And now the same winning condition as before. Obviously, we want to satisfy Fi, and we want to satisfy the so-called filtering set E. Okay. And what our goal at the end of next lecture is to have proven something like the following, that if a CNF formula F admits an S delta E polynomial calculus expander with overlap L, then the degree of refuting F is strictly larger than delta S over 2F. This is our goal. So, and this is a good place, I hope, I believe, I think, to take a break. So why are we doing this? Why am I presenting it in this way? I mean, you can present these results in different ways. What I like with this formalism, and why I'm torturing you with this formalism, is that it is one way of seeing how similar, but at the same time different, resolution and polynomial calculus proofs are. You build the graph in exactly the same way. You can say that the graph is nice if you can play this stupid combinatorial game on the edges. It's even the same combinatorial game, but you're just saying, well, if you want an algebraic lower bound for the polynomial calculus proof system, then you have to go first. And now it's kind of clear in this game. I mean, in the resolution game, why could we do Tsetin? Well, it was obvious, right? The adversary plays, and then we know that, oh, I have to satisfy this parity constraint, but luckily I have control over a variable in the parity constraint. So if the constraint is satisfied, I'm good. Otherwise, flip the variable. Not too hard, right? And if I wanted to do the pigeonhole principle, I first got an assignment that was a partial matching because of the filtering set. And then I had to make pigeon I happy. And basically, I just looked at what, and I have control over the whole axioms, over the whole variables in whole J. So it's kind of clear, how could I make the pigeon I happy? Well, either it's already happy and then we don't need to do anything, or if it's unhappy, then I send it to whole J. What's the problem? Well, the problem is someone else could have gone to whole J. But I have control over the whole, so I just say to all other pigeons, sorry, your whole J is occupied. And then they become very unhappy, but the game doesn't care. The game only cares about pigeon I. And the point is, if the adversary goes first, I can patch things up. But now suppose I wanted to do this with this game. Same thing is kind of ridiculously obvious how impossible it is, right? I know I have to satisfy this parity, and I get to set one variable in the parity, and then the adversary gets to set the rest. I mean, it's a non-starter. Similarly, for the pigeonhole principle, I have to make pigeon I happy. What can I do? Well, I'll send it to whole J. But of course, the adversary is not stupid. I mean, the adversary will just make sure to send some, do something else stupid. In particular, maybe the adversary, if I were an adversary, I would take pigeon I and send it somewhere else also. Or something like this. So you have to think a little bit, it depends a little bit, or at least, okay, so I'm not saying this very well, and I realized I shouldn't have gone into this discussion now because it gets a little bit more complicated. But basically, if you try to set things up so that you can play the polynomial calculus edge game for some representation of the pigeonhole principle graph, it's not going to work. And that is why this illustrates somehow why for Tsetin and for onto functional pigeonhole principle, we have resolution lower bounds, but we don't have polynomial calculus lower bounds. So when we get back after the break, we are going to look at, we have this small example graph that we played on last time. So maybe we're going to refresh our memory about the resolution edge game and then just quickly play a round of the polynomial calculus edge game. And then we are going to start proving this theorem, except it's complicated. And a lot of it can be shared with resolution. So we're actually going to we're going to reprove this theorem we did last time again. But we're kind of going to do it in the way we proved the lower bound for polynomial calculus. And it will be, so you'll see the same proof again, except it's going to be more complicated and more confusing. And still, ultimately, it's going to fail. But that means that when we reconvene next time, we already have like half of this proof in place. So we'll keep everything from here that was good and then work even a little bit harder, and then we'll get polynomial. That's the idea. And one more thing that we'll do is, in the process of proving these theorems, we will strengthen them a little bit, because you could say, well, what if I'm able to build this graph and 99% of the edges are good, but I lose on some edges? Like, can I not get anything then? And the answer is no. You can still get a lower bound. Like if most edges are good, or sufficiently many edges are good, you can still get lower bounds. And we're going to define a version of these theorems that take care of whether edges are good or bad. This is the plan after the break. Any questions before we take a break? Okay, so we're back after the break, and I just want to talk briefly about these games that we're playing. So we've come so far that somehow when we're given a CNF formula later, these are going to be, by the way, I mean, this is a CNF formula, but if it were a set of polynomials, I could also have just have labeled like W or X or Y. That's just this monomial W, X, Y, not Y or X. Well, that's just going to be, I guess, that would be X minus YX, unless I'm screwing up. Y or not X, that would just be Y. U minus not X is, I guess, U minus UX. Is that right? And that looks suspiciously similar. What am I getting wrong? No, but they were the same.
No, you had U and X.
1 minus U times X. Here I have 1 minus X times U. I guess X minus UX.
No,
wait,
they're similar.
What am I?
It should have been, I think it was
They
U.
were different initially.
They were different. Okay, sorry. Too early in the day for this. So basically, I'm going to be, from now on, also for the rest of the lecture today and probably also going forward, whenever we have like, whether are we talking about W or X or Y, or are we talking about W times X times Y? Are we talking about not U or X, or are we talking about X minus UX? I don't care. They're kind of the same. And in particular, I don't push me too hard on this issue because I'll screw up the translation, right? I already proved this beyond any reasonable doubt. But the point is, sometimes when I talk about polynomials, when I talk about clauses, they're kind of, clauses are just a special kind of polynomials. But to the extent we talk about 0-1 assignments, true always means that the object should vanish. It should evaluate to 0. Okay, and what we said is that now if we have a CNF formula, for instance, like this, and you build a graph like this, then we want to prove a lower bound. We want to be able to do two things. We want to be able to argue that the graph is an excellent expander, which is not the case here, but never mind. And then we want to be able to win the edge game. And it should be clear that the resolution game is strictly easier than the PC game, because it's the same game, but I switched the order of the players. So we already talked about last time, I think, that we cannot possibly win the satisfier on edge F1 V1, because satisfier could just play to falsify the U or X clauses, and we cannot flip those variables. We also said, I think, we cannot win on F1 V2, and the reason for this was that the adversary would play Y being false, and since we cannot change Z, we have to keep Y being false, because otherwise we have an invalid assignment. But then if you set Y to false and look what happens here, and look at what the adversary might play, then the only way of being guaranteed to satisfy all the clauses is to set X to true and false at the same time, and that was not possible. We did talk about the edge F2 V2, and the reason we could win that edge in the resolution game is that the adversary goes first and plays something, and then we're not going to change Y because we're worried about the so-called filtering set. But we can change X, and we're just going to play that X is the disjunction of Y and Z, according to the adversarial player. So if you just set the truth value of X to be Y or Z, then we win, because these clauses encode this. Okay. But in the PC game, so if we're playing on F2 V2, the filtering set, we don't have any choice. Note that we're playing XY, so we're going to touch this clause, so we have to play Y to false. Right? The satisfier have to play Y false. And then we just look at F2 with the restriction that Y is set to false. The first clause is satisfied and disappears. The second clause is not affected. We get X or not Z. The third clause, Y is false. We got not X or Z, right? So somehow we have to play on X so that when the dust settles, we will have satisfied these. But that is saying that we have to play, if you look at what this says, it says that we have to play X so that X takes the same value as Z. Only the problem is that someone will choose Z for us when we're done. Okay, so in the PC game, we're going to lose on this edge. Let's see an edge on where we can win. It's going to be a little bit of a stupid example. So again, in the PC game, it turned out that actually this wasn't a good edge after all. So let's play on this edge instead. And I claim that that's going to be a good edge. And it's a little bit of a ridiculous example, maybe. There are more interesting examples that you could imagine. Basically, the point is that on F3 V2, I can play, what can I play? I can play Y false. This is sort of what I have to do. And then I just play X true as satisfied. And now it's kind of clear that I won because, well, there's only a single clause in here, and that's satisfied. And also, actually, I fixed all of F3 to true. So now we're good. So what I have to do, if you think about it, like in order to win, I always have to fix all of these. I have to nail all of these clauses to true. Here, I don't necessarily have to fix all of them to true, but either I'm fixing them to true or I'm not allowed to touch them at all. Yeah. And now what we want to prove now is that if I can build a graph like this that is an expander and so that most edges are good, then I will have resolution or polynomial calculus lower bound. So we're going to first just define the notion of what a good edge is. A good edge is an edge on which I can win the game. And just to follow the terminology in the Mikša and Nordström paper, yeah, I'm just going to stick with that terminology. There's the terminology of respectful neighbors and respectful edges. And whenever you see something that is respectful, that's code for polynomial calculus. Something that is semi-respectful, that's code for resolution. Okay. I don't know if it's the greatest terminology on planet Earth, but it is what we wrote in the paper, and I'm going to stay consistent with that. So let me quickly do some definitions just to try to define what it means that an edge would be good. And from now on, by the way, we're going to do polynomials now. And just to stress that we're doing polynomials, this guy is going to change its name. It's going to be a Q, because QE looks like a clause set, but Q looks like a set of polynomials somehow. Not exactly clear why, but somehow that's how I feel. So the first notion is this thing we already talked about, like a good assignment, a respectful assignment with respect to polynomial calculus. You know, rho is respecting the polynomial set Q if either, for every polynomial, either it sets the polynomial to true, or if it doesn't, then it doesn't touch it at all. So either you hit and kill the polynomial, but you don't hit and miss, or partially wound the polynomial. Like either a clean kill or leave it undisturbed. What do we mean by rho satisfying Q? Well, now rho could be a partial truth value assignment, and then you have to think a little bit. Let's just say that basically rho satisfying Q means, well, rho assigns values to variables. You just plug in these values, simplify the polynomial, then take cancellations. And now if everything cancels so that you have a zero, then it's natural to say that that is what it should mean, that a partial truth value assignment satisfies a polynomial. That is the same thing as saying any way of extending rho to a total assignment would make Q vanish. Okay? Are you happy with this? I'm not going to labor this point so much. Okay, so this is a respectful assignment. And then just to say that a set of variables, which you should think of a possible domain of a row, a set of variables, because these are the sets that live on the right, a set of variables respects a set of polynomials, which are the guys that's going to be living over on the left. If there is a row that you can... So as sometimes happens, it seems we had a small technical hiccup. So we're rewinding a little bit to try to make sure that we're not missing anything. So we just played, hopefully, even also on the recording, we played successfully the game on the graph with vertices and edges. Now we're trying to make it formal. So our first definition is we're looking at the partial truth value assignment row. We're looking at a polynomial set Q. We say that row respects Q if for every polynomial lowercase q in capital Q, one of two things hold. Either row satisfies Q, so that Q vanishes completely, or row doesn't assign any variable in Q. So the domain of row intersect the variables of Q is the empty set. So what does it mean that rows satisfy Q? It means, because row is now a partial truth value assignment, it means that we take all the values that row assigned to the variables, we plug them in, we simplify Q, and then we take cancellations. And if that makes Q vanish, that's the right definition of saying that the partial truth value assignment row satisfies Q, because this means that any total assignment extending row will have to make Q vanish. Okay. So this is what it means that a partial truth value assignment row respects a polynomial set Q. And now, and what we're going to have polynomial sets Q, why are we talking about them? Well, because polynomial sets are what we're going to have here over on the left-hand side, and we're going to have it also in the filtering set. And we're not going to have rows in the graph, but we are going to have variable sets on the right. And so let's say that a set of variables V respects a set of polynomial Q. If there is a row with domain exactly V that respects the polynomial set Q. So a variable set respects Q if there is a way of setting the variables in V so that for every polynomial in Q, you either satisfy it or you leave it untouched. This is the notion that we will need for the polynomial calculus graph. For the resolution graph, we're going to have a slightly more relaxed notion. We're going to say that V semi-respects Q if for any sigma that you set to all the variables in Q except V, I can set the variables in V in such a way that Q gets satisfied. This is what this means. You take Q, you hit it with the partial assignment sigma, and then you set the variables in V that sigma weren't allowed to set, and then Q should be satisfied. Now it should hopefully be somewhat clear, maybe, that this corresponds to, you should think of sigma as what the adversary plays, and then rho is what we, the satisfier, play. And here we're using that we see sigma when we play our rho. And this definition is capturing that we don't see sigma. Sigma will only be played after the fact. Is this making sense? Okay, and this is the final example that we're going to have. So suppose now we have a set of 4 clauses, x1 or x2, not x1 or x3, x1 or x4, not x1 or x5, which I hope I successfully translated to the polynomials x1, x2, x3 minus x1, x3, x1, x4, x5 minus x1, x5.
There is an additional constraint on sigma, right? Which is that it can be extended to a satisfying assignment. Like sigma is not trivially, but
we'll get. I think I'm happy with what I have right now. Oh wait, did I forget something?
I'm just asking what.
Oh yes, a technical thing for the respectful thingy. Okay, so Q. I think. Thanks. I'm sorry. I think you're right. I'm wrong. I think you're saying this, that Q. Just let's rule out the stupid corner case. Q doesn't contain constant polynomials. Why? So a constant polynomial like the polynomial 2 or 5 or whatever. because in our world, this is sort of contradiction already. And if in our, and Q we should think of as being part of the input, and if the input already contains a contradictory constraint, then we cannot prove any lower bound. Then you're just going to look at this polynomial and you have contradiction. So this was what I was missing. Yeah.
I think there's also, for the definition of summary space, you're saying if for every assigned sigma, there exists a row. But what if I pick sigma such that it sets a monomial to 1? Like what if sigma is locally bad?
Oh, but I'm not allowed to do that. That's the point. So I think, no, I think I'm happy with it because the adversary is not allowed to play a sigma that violates anything.
Where is it written?
No, it's
Okay.
not written anywhere.
Okay, sure.
It's written here, right?
Sure.
Oh, wait, hang on.
It should be at least extendable. It should be at least true that there exists.
Um,
You're saying if sigma just like screws everything.
no.
Locally.
Can I fix this online? I see what you're saying now. I think
It's fine.
maybe it's fine. Let's take it offline. We're
Okay,
not.
it's fine.
I'm not going to stress the resolution
Okay.
part. I think it's fine
It's fine.
for the. Let's say that it's fine for now,
Mhm.
and let's keep it in the back of our minds. Okay, so now I just want to say that the variable set v2 is respectful vis-a-vis q. And the reason for this, I'm gonna set x4 and x5. I just said the proof is, how can I prove that it's respectful? Well, just give me an assignment. And I think I'm gonna set the x4 and x5, both of them to true. Because that means that both of these polynomials vanish, and I don't touch these polynomials.
Noel is asking for a slightly larger font size.
Okay. So also Q is not visible.
It is visible, but it's a bit hard. So for the, going forward.
Okay, so let me read it out. Just that if I set x4 and x5 to true, then x5 minus x1, x5 vanishes. x1, x4 vanishes. And these are all over just x1, x2, x3, so they're unaffected. Okay. B1 is not Q respectful. And the reason for this is I have to set x1. And that means that I would have to make, and x1 appears in all polynomials. So that means by setting x1, x2, x3, I would need to satisfy all polynomials. But clearly I can't do that because this polynomial, x1 or x4, wants x1 to be true. X1, not x1 or x5, wants x1 to be false. Okay. What about semi-respectfulness? I'm not going to talk about it because let's focus on polynomial calculus. If you get the respectful stuff, then that's it. Okay. So P and Q now are going to be sets of polynomials in what follows. Fixing some notation. V is going to be a polynomial, a set of variables. Just to, how should you think about this? You should think of P as being one of the vertices on the left. You should think of Q as being this mysterious filtering set down here. You should think of V as being over here. So now we're getting to we're defining now, think of PV as being an edge, and we want to know whether the edge is good or not. So we'll say that P is Q respectfully satisfiable. if V respects Q, as shown by a row that is Q respectful. So rho doesn't necessarily satisfy Q, but it either, for all the polynomials in Q, it either satisfies them or leaves them untouched, and it satisfies all of P. Okay. So what is rho? Rho is what I would play as a satisfier, right? And basically, I'm saying that P is Q respectfully satisfiable by V, or PV is a respectful edge, if the satisfier can win, and rho in this definition is the move that I would make. For resolution, I get something simpler. I just say that P is Q semi respectfully satisfiable. By V. If V semi respects P union Q. And I claim, but I'm not going to stress it too much. The idea is that somehow that we really care about this polynomial calculus definition. This is meant to capture the resolution definition. Where the adversary plays first, and then I get to flip V so that I should satisfy P. And the thing that we maybe need to take offline as homework is that, does this definition really capture that the adversary has to satisfy Q? I think this is the definition that you and I patched together after the last time we did this.
There is a problem in what you touch. Like, what if the initial sigma touches things that variables of rho cannot touch, and it just screws it up there? Like sigma creates local.
Yes, exactly. So we're not allowed to do that. So maybe we need to patch the definitions a little bit. So what we're going to do now is the notation we're going to do from now onwards is, oops, something funny with this board. We have a set of polynomials again, which could be a CNF translation with fancy style P over variables V. We're going to partition P into Q union I goes from 1 to M PI. And this is what I'm going to refer to as fancy style U. This is the left-hand side U of my graph. And then I'm going to divide the variables up into I from Y goes to N BI. And again, I want variables to occur in a bounded number of variables. And the way I now define, so this is the last time we see this definition that we've seen before. How do we define the graph? Well, again, the left vertices are going to be PIs. The right vertices are going to be VJs. And the edges, again, are just, once we've decided on this, we get edges well defined. PV is an edge precisely when the variables in the polynomial set P intersect V. And now, I need to erase something. So let me erase the theorems that we're going to prove. This seems like a great idea. So now I've defined the graph. And now I just say that P and V are Q respectful neighbors. Or I say that the edge is respectful if P is Q respectfully satisfiable. What does this mean? Again, this means that I can assign variables in V to satisfy P and to satisfy or leave untouched everything in Q. This is the polynomial calculus definition. The resolution definition is the semi-respectfulness. Full neighbor. Well, the same thing. If P is Q semi-respectfully satisfiable, which, again, what we're trying to capture and what we might need to touch up in the lecture note afterwards, this is just meant to say that we're given an assignment. Yeah, so the way to patch the assignment, right, is to say that
Could start with the satisfying assignment, and you want.
I think we could define like a sigma prime that sets also V, and sigma prime should satisfy Q. So for any sigma prime that actually satisfies Q, I pick out sigma to be the part that sets the Q, that sets the Q variable without V. And then for any such guy, I should be able to pick out V, a row that sets Q under sigma. I think something like that should work. Because now, basically, I'm starting with something that sets all of these variables and that satisfies Q. And then I'm allowed to change things on V. So basically, all I'm trying to capture again is the adversary goes first. He's going to place some kind of assignment that satisfies all of Q. And I get to modify that assignment on V.
Or with this definition, why doesn't rho just play the rest of sigma prime? Why doesn't just rho go back to the initial thing?
I think that would be fine.
Okay.
Okay. So with this, okay, so we've now gotten to a point where we are almost done with the graph. So the whole point is now that what these definitions about respectful and semi-respectful neighbors, what we're trying to capture is that whenever we're able to win the resolution game, then we have semi-respectful neighbors. So for instance, F2 and V2, they were semi-respectful but not respectful. Okay, and this was like a fully respectful set. And the point is, we're never gonna, I should have said this long ago, we're never going to mix the two concepts. Like we decide ahead of time, are we doing resolution lower bounds today? Then we only have semi-respectfulness. Are we doing polynomial calculus lower bounds? Then we only talk about respectfulness. So the reason that we're doing the development in parallel is to just see that's why we're sometimes able to do resolution lower bounds and not polynomial calculus lower bounds. Okay. And we're almost done. Just two more pieces of notation. Now, suppose I have a set of left vertices u prime. Then let me say that the Q boundary, this is like the respectful boundary, is you first look at the graph and you pick out all the unique neighbors. And then you filter out and you say, I'm only interested in the neighbors with respectful edges. So that is going to be my notion. Like a graph that is a good expander if first I demand that the unique neighbor expansion should be good, but I only count the unique neighbors that are actually connected with respectful edges. And if I want to, this is what I need for polynomial calculus. For semi-respectfulness, I will again do exactly the same. I pick out all vertices that are unique neighbors and that are connected with semi-respectful edges. So this means that if you're in this boundary set, firstly, you're still a unique neighbor. So like if a vertex that is connected with one respectful edge and one disrespectful edge is not a unique neighbor because it has two edges. So you're only picking out the unique neighbors. And then you're saying, oh, and in addition, I only care about unique neighbors on which I'm able to play the game. Okay, and now finally, we can write down what properties we want from the graph. So here is the graph now. Polynomials in U, variables in V, filtering set Q. I say that this is an, okay, so let me state the full theorem. These are like the full theorems, and then we're going to prove slightly simplified versions of them. I'm going to have an extra parameter C that I'm going to explain, and then we're going to remove it. So let me say that this graph that I built now for polynomial calculus is an S delta C Q respectful boundary expander. If two things hold, if the following holds, that if for all U prime, all vertex sets on the left that are not too large, the expansion guarantee is still S. For all such set, it holds when I look at the boundary expansion, counting only good edges. Then that should be at least a factor delta of U prime, except I can allow myself an additive like C if I like. Yeah. This is the expander object that's going to work for resolution. And the graph is again an S delta C Q semi-respectful boundary expander, that is a resolution expander. If the same holds, but again, for all vertex sets that are not too large, if I look at the boundary, but now I have a slightly more relaxed requirement on my edges. I'm looking at the semi, I don't need fully respectful edges, only semi-respectful edges. If that is larger than delta times the size of the set, minus possibly the slab. I'm pretty much going to remove this slack right away. I'm just going to say that there are some settings where it's convenient to, sometimes it's hard to get really small sets to expand. Why do we need small sets to expand? The only reason we need small sets to expand is to argue that small sets cannot be contradictory. But often we can argue by other means that small enough set of constraints are satisfiable. And then we don't need this. So there are now two versions, basically, but I feel like I wonder how much we can take of this. So maybe I'll just state the corollaries right away. So basically, what I'm going to claim now is if you can build a respectful expander, and that is a true expander, there is no slack, then you have a PC degree lower bound, polynomial test, and we can go home. If you can do it, except that you're getting slack like 1 or 2 maybe here, then if you have a separate argument, then the only thing that doesn't work is that, well, you need to be able to argue that small sets cannot be contradictory. And if you have a separate argument for that, then you still get your lower bound. This is the resolution version. What we did last time is we said we just had an expander, then we got it with lower bound. And then you're just saying in some settings, you could say, well, maybe if I have an expander, except that I'm losing a little bit in the expander for small sets, but I can argue via separate means that small sets cannot be contradictory, then that's good enough. Okay, so now let me maybe state the statements without slash. So suppose that a CNF formula F admits an S delta no slack, so it's really an expander, but it's semi-respectful. Okay. Then once I've built that object, I'm home, then my lower bound is expansion factor times expansion size guarantee divided by 2 times the overlap. If a set of polynomials P admits an S delta, and let me fix 0 right away, Q respectful expander, then I can say something stronger. I get degree lower bound. Exactly the same bound, delta times S over 2 times the variable overlap. Okay. And the point is that almost all polynomial calculus lower bounds in the literature you can get by just building a graph like this and then plugging this there. And this is what we hope to prove next lecture, where we will probably make a recap of all of these definitions. This we already proved. Okay. Except I was thinking that it could make it easier to prove the polynomial calculus result if we reprove the resolution result again. So that is how I want to end the lecture, by doing this. Because okay, so what do I want to do now? I want to focus on this. Suppose we built this object. The difference from last time is that not necessarily all edges are good. but we know that enough edges are good that when I look at a medium-large set, there are many good edges that go out to unique neighbors. And I want to argue that that will give me a resolution with normal. Okay. And what I want to do is, again, the point of doing this again is we'll set up the machinery, somewhat similar, I guess, to how we did it for click. We'll set up some machinery that is ultimately not quite strong enough, but most of it is good. And that will allow us to recycle. So firstly, we're going to define the neighborhood of a clause. So think of C as any clause. I'm doing now a resolution proof. Basically, what am I going to do? One way of doing this, if you think about it, is I'm just going to argue, give me a resolution derivation that is in at most this length, not strict, like less equal this width. Okay. What can we say about a resolution derivation starting from F that is in width less equal delta S over 2L? Well, we can say that it should only be able to derive satisfiable things. Okay? So I'm going to look at all clauses derivable from F in not too large width, and I want to argue that those clauses are satisfiable. They're not contradiction. Okay? So let's look at such a C will sort of, you should think of from now on, think of C as such a clause. Okay? So the neighborhood of C is what we get is, suppose if I just throw in a vertex set containing only the clause C on the left-hand side. Then I know by the definition of the graph which edges it generates. What edges would it generate? Well, it would generate an edge to all the vertex set V such that vars C intersect V, right? So this is like if I have built my graph and I'm throwing in an extra vertex for C, the neighborhood of C is like what edges would occur. So I could think about any clause and define a neighborhood like this. And now I want to understand, suppose that C was derived, what can I say about the sets of clauses that could have been used to derive C? Well, any clauses or polynomials that contain variables in C, that's fine. But suppose that the clauses contain other variables that are not in C, then they must have been resolved away, which means that there cannot be sort of a unique clause somewhere containing a variable that is not in C. If I use the set of clauses to derive C, then sort of the variables that are no longer left in C, they must have been resolved away, so they cannot have been in unique neighbors. Because if variables sort of occur only in a single constraint, then there's no way of getting rid of them. So this is the intuition for, I'm going to look at a set U prime of a subset of clauses or polynomials. And I'm going to say that it's SC semi-respectfully contained, semi-respectfully because we're doing a resolution. And then I'm not going to have the energy to say semi-respectfully. So from now on, I'm just going to say that it's SC contained. If two things hold, the set is not too large. And if I look at the boundary of U prime, it's contained in the neighborhood of C. So I look at all the variable sets that have a unique neighbor in U prime, but they also have a neighbor in C. Otherwise, it would be very, basically I'm saying if this holds, then it's conceivable that I would have used U prime to derive C. But if this condition is violated, then somehow there's a variable that I got rid of somehow, and it's very hard to understand how I got rid of it. Okay. Before, when we did our proof the last time, what I'm trying to do now is for every clause C, I want to define a set of clauses or a set of polynomials that I believe is maybe responsible for deriving C. The way we did it last time is we picked the smallest possible or a smallest possible set that implied P. Okay. That's sort of the minimalist approach. We define the complexity measure to be, let's pick out the smallest possible set, the size of the smallest set that implies C. Now I'm going to go a maximalist approach instead. I'm going to throw in, like, what's the largest possible set potentially that could have been used to derive C? Except, well, all of the formula could have been used to derive C, and that's kind of the wrong answer. So, like, what's the largest possible set, but not too large? This not too large part is this. Okay. So I don't allow the set to contain more than S vertices, but if it doesn't contain more than S vertices, and if all the unique neighbors are contained in the neighborhood of C, then I'm saying, yeah, maybe I used U prime to derive C. Okay. But there could be many such sets, right? So I'm actually going to do one more level of maximization. And I'm going to say that the support of C, the S support of C, is going to be the union of all SC contained sets. So this is now going to be like, you know, this is U prime was potentially a set that could be used to derive C. Let me take the union of all such sets. Okay. And now what do I want? This is the object that I want to operate with. I want to prove two things about this. Now, our game plan is the following now. And if I can execute this, then we're going to be done. Okay. First thing I want to argue is that the support of C is not too large. Okay, it's somewhat large, but not too large. And it is indeed possible that I used it to derive C. I'm going to argue that if I take this support, all of the clauses, all of the polynomial in it, and I throw in this filtering set Q also, then that implies C. Okay? These are the two things that I'm going to prove. Okay. If we can do this, I claim that we're done. Why are we going to be done? Well, because we're going to argue that this set is not too large. And basically, because of the expansion argument we did last time, that means the sets that are not too large, they cannot be contradictory. So this set is satisfiable, and even if I throw in Q, it's still going to be satisfiable. This requires an argument, but it's going to be because this set is not too large, and because of we built successfully an expander. Okay? Okay, good. Suppose that you're buying that this union U is satisfiable. Why should that make us happy? Well, this set implies C apparently. And it has a satisfying assignment. Okay, so plug in the satisfying assignment alpha here. Well, that assignment apparently also satisfies C. What does that tell me? Well, it tells me that C isn't contradiction. Okay, but that's great, because if I prove this now for any clause C that was derivable in width at most this, basically for any clause derivable in this width, I found a satisfying assignment. So it's not contradiction. So any derivation in less equal this width is apparently not deriving contradiction. I'm not sure, how happy are we at this point, or how tired are we at this point? There's some happiness. Or should I say the high level thing again? So basically we defined this measure in some weird way, but this was just a definition, right? I mean, once I fixed my graph, I looked at a clause, and I just say, look at all the variable sets that intersect the variable of this clause. This gives me a set of vertices on the left. Now, in my graph, I just look at all sets U prime that are not too large, and when I look at their boundary expansion, they're inside this set NC. Okay? Then I say, oh, U prime could maybe plausibly have been used to derive this clause. And I take and then since I don't know which U prime I want, I just take the union of all of these. And then if I can show that, yes, indeed, it's enough to imply C, and the set is satisfiable, then C is a satisfiable clause. Then I don't have derived contradiction.
I have a quick question.
Yeah.
So this union, is this like, we're taking the union of all of the sets, so why couldn't we just choose all these U primes to be size 1, and then all of the neighbors of it are unique, and then it's
Well, you want, if you choose all of them as size 1, the point is that why do you want U prime to be larger? Because once you pick it larger, you're able to cancel out stuff. Like everything has to be inside. The neighborhood of C could be pretty small. So if I pick, like, it could be that U1 prime has unique neighbors outside. U2 prime also has unique neighbors outside. But if I take their union, then their unique neighbors outside of C sort of cancel out each other. Is that addressing your question?
yes.
So that for that reason, I might want to like pick U prime slightly larger. But then on the other hand, we know we're in an expander. So like if I pick U prime somewhat large, I'm also going to pick up lots of unique neighbors. So it's sort of, yeah. But definitely like picking individual guys, then I would expect it to be very small to satisfy. Very hard to satisfy this. Okay. So, okay. So I have 2 lemmas left now. So actually, I am going to claim that take this set that is the union of all SC contained sets. Okay, this humongous union set is itself SC contained. In fact, I can say better, it's S half C contained. So actually, I'm just sort of fooling you. Take the union of all the sets, and it turns out that it's actually one of these sets. Okay? But this is the nicer definition, and then I just argue that in fact, it is a contained set. Why is this true? Well, first, so what do we know? We know that the support is a union of SI contained sets, UI. Okay, so let's fix just one set UI. What do I know about it? So I know that the boundary is at least that large, and that's because of expansion, because this set is small enough. So let's just turn it around. This means that UI itself is less than the size of the boundary divided by sigma. How large is the boundary? Well, all of the boundary is contained in the neighborhood of C, right? Because it's SC contained. So UI is not larger than the size of the neighborhood of C divided by delta, just by definition. Okay, let's keep working on this. How large is the neighborhood of C? Well, look at all the variables in C. All the variables, every variable could potentially contribute neighbors. How many neighbors can every variable contribute? Well, the overlap at most, right? I know every variable occurs in at most overlap distinct sets. So this is going to be at most, and the number of variables in C, that's another name for the width of C. The overlap is our parameter L. Okay. And now the question is, I forgot to add that, of course, we're looking, suppose that C is a clause of that is not too wide. Okay. We're looking only at narrow clauses because this is the, suppose that C is a clause in the derivation. That means that it's particularly at most this wide. Okay. So I need an upper bound on the width. That's what I'm going to plug in here now. Then I get delta S over 2. Okay, are you with me? Okay, but now I have an upper bound on U in terms of neighborhood of C divided by delta. The neighborhood of C, size of this is at most this. This is telling me that UI is at most this large. So I used, what did I use? I used that we have a good expander, but the boundary expansion is contained inside the neighborhood of C. And since the expander is so good, that means that UI cannot be too good.
Good question. So I mean, isn't this basically saying that if it is SC contained,
then it's
S over 2.
S over 2 C contained. Yes.
There's nothing.
Isn't this sort of like a, can't I make it S over 4 C contained and then S over 8 C contained?
No.
Maybe I'm missing something then. Why?
Because you only have the bound of the width, right? Like how do you make it?
Oh, S is fixed. Okay. Yes. Okay. I see. No.
Yeah. So this, I mean, yeah. Like I cannot. I think what just but like yeah. I would need to get in. I guess one way of viewing it is that somehow if you had. I mean, I only have the upper bound on the width of this, and I cannot like start decreasing that. The only thing I know is that the clauses have width at most this, and then I can use it in one shot. But this bound is never going to change. Okay. But now you realize that now I claim that if U1 and U2 are S contained, then so is U1 union U2. Okay, why? Well, firstly, U1, if U1 and U2 are SC contained, then they have size S over 2. So this means that the size of their union is at most S. So that's great. The size is okay. Now we need to look at their boundary. So what is the boundary of U1 union U2? It has to be inside S. But now you realize that this is somewhat related to the very well-timed question. What can happen if we know something about the boundary of this guy, and we know something about the boundary of this guy? And when you throw them together, the best thing that can happen is that you sort of pick up the union of their boundaries, but nothing better can happen. You could have cancellations. You could have unique neighbors in here that are also unique in here so that you lose stuff. But it's definitely going to be the case that the boundary of the union is contained inside the union of the boundaries. Okay. So, or in symbols, the boundary of U1 union, the boundary of U2 definitely contains this. Okay, but both of these guys are contained in the neighborhood of C by definition. So now we see that if U1 and U2 are SC contained, then so is their union. Which means in particular, how large is this union? Well, at most size S over 2. So by induction now, you just induct over all of these guys. Throw in set after set after set, and all of the time the size is at most S over 2. Okay, but then actually we're almost done. Because all I need to prove now is the second lemma. Okay, that says that suppose that pi is a derivation from fancy style f, and suppose that the width of pi is at most delta s over 2L, then for all clauses in this derivation, it holds that if I look at their support and throw in Q, that every clause in the derivation is implied by its own support. Okay, and then one thing I feel like we're getting a bit tired, so let me maybe just do some high-level stuff here. One thing that we're going to miss is, well, we need to argue why this is a satisfiable set. But this is exactly what we did last time. Remember the peeling argument towards the end. So I claim that the fact that these not too large sets are satisfiable, we already did this last time. It's going to be exactly the same proof. Okay, but I do need to prove this. This is going to be by induction. So there are two base cases. And let me maybe focus on the more interesting stuff. So let's do the base cases quickly. So base cases are axioms. If C is in the filtering set, then I think we can agree that this holds. Okay. Suppose that C is in some set F that is one, otherwise if C is not an axiom, then it lives in exactly one left side vertex F. Okay. And now I'm just going to argue that F itself, this set, is SC contained. So it's in the support. So definitely implies C. Okay. And basically, how would you prove that? I think I'm going to skip this maybe. Suppose basically you're going to take the only thing that could fail is if there is a V in the neighborhood of F. What would make us nervous if we find a V that is not inside the neighborhood of C? Okay. Sort of if all the vertices in the neighborhood of F are inside the neighborhood of C, then this is SC contained. I mean, this is a set of size 1, so we're good. But what would it mean if we had a V in the neighborhood of F that is not intersecting C? That means that V is a set of variables that doesn't even talk about the clause C. That means that if we're going to play on this edge, then in particular by playing on this edge, I would need to be able to satisfy C, but that's going to be really hard if the vertex that V doesn't even intersect C. So it's not going to be a respectful edge, so it's not in the respectful boundary. And this is like, there's nothing fun happening, really. Okay, so let me go to maybe what is slightly more fun, namely the induction step. Okay, so by induction, so the induction step is that C1 and C2 derive C, and by induction, we know that the support of Ci for I equals 1, 2, union Q implies Ci. So therefore, the support of, I'm getting a bit tired about all these indices, so let me write it without indices. And if I take the union of their supports and Q, then by the soundness of resolution, this definitely implies C. Okay, so let me give this a name just because I'm tired of typing. Let me call this fancy style S. So clearly, what can I say about fancy style S? Fancy style S union Q implies C, and fancy style S has size at most capital S. And now let me say that if S is any set such that it is not too large, and S union Q implies C, okay, then we're going to prove that actually S intersect support S SR of C union Q implies C. So this is somehow saying, suppose you give me any not too large set S that implies C, then somehow, well, the explanation for this is just in the support part. Like there's nothing in S that you really need except for the support. So this was our maximalist approach, right? Anything reasonable we could think of that would be useful for deriving C, we threw it in. And indeed we succeeded. Like if you give me any not too large set that implies C, then you only need the support of S as the support of C. Okay, and if I can prove this, then clearly in particular the support of C union Q implies C. Okay, so we're really running out of time. So I'm debating with myself a little bit if I can just say something quick why this works. So basically what I'm going to do is suppose well, if by happy coincidence S was already contained inside this, then we would be good, right? So we're only worried about fancy style S not being contained inside the support. So what I'm going to argue is if this holds, then I'll find some vertex set to remove from S while maintaining this implication. Okay? If this holds, but S is not contained in C, then I'll remove something from S and the implication still holds. Okay? And now if S is still not contained in C, I'll just keep removing stuff. I mean, S is a finite set, so sooner or later we're going to be good. Okay? So the only thing I need to sketch now is how will I do this? Well, suppose that S is not contained in the support of C. Why is that? You know, that's in particular, note that S is actually a candidate set for being SC contained because S has size at most S. So the only reason why S fails to be inside the support is that there is something in S, something in the boundary of S is outside of this, right? So there is a V in the boundary of S that is outside the support of C. And fix FV to be the edge for f, v, and s. And now we're going to play this game again. We're just going to say, okay, fine. Look at S. And I'm claiming that you can remove FV and still have this implication. Suppose not, okay? We're really close to finishing now. Suppose not. Well, if not, then this holds. Okay, what am I going to do now? So that means that there is an alpha. There is an alpha that satisfies this, falsifies this, and falsifies this. Because otherwise it wouldn't be a non-implication. But this is an edge, and it's in the respectful boundary, so we can play the resolution game on this. So take alpha, that's a valid move from the adversary. And now just by reassigning V, I will satisfy F also. So now I'm suddenly satisfying this and this. And by the rules of the game, I'm also satisfying this. But V, by assumption, is not contained in C, right? So in particular, V doesn't share any variables with C. So this is still false. But I started out, but now I'm satisfying this, and I'm satisfying this, and I'm violating C. That's impossible. And now I'm done. And again, the notes will have this in a bit more detail, but really what we're identifying is we're building an expander, and we're just using this fact that there is some kind of set Q that restricts which assignments we're interested in. And then we're just saying that for every edge, we can change the variables on the variable side to satisfy all the constraints on the constraint side and keep Q happy. And then we're just using boundary expansion, this miraculous thing that since this V was a unique neighbor of FV, we can fix this without changing the rest. And this is just the argument that keeps recurring over and over again. Okay, so two final questions to think about. Did we do anything in this proof that we were using resolution instead of polynomial calculus? Or would all the arguments that we did work for polynomial calculus also? The answer is, yeah, we're only using soundness of the proof system. Okay, so why doesn't this give us a degree lower bound? Well, because we're actually, if you think about it, what we're doing, let's see if we have it somewhere on the board. At the end of the day, the quantity that we're able to bound, we're able to prove that as long as this quantity stays small, we're not deriving contradiction. So any proof by contradiction, this quantity gets large. That's what I prove, right? In any proof that derives constraint C, such that the number of variables in C is small, I'm not deriving contradiction. Okay, now happily, what can I say about the clause that contains many variables? It has large width. What can I say about the degree of a polynomial that contains many variables? Not too much, right? Maybe it's x1 plus x2 plus x3 plus x4. That's a degree 1 guy that contains arbitrarily many variables. So all of what we've done works for this object. So we're lower bounding the variable set size for the objects we're deriving, but that is not good enough for polynomial. So we have to work harder. And that's what we'll do next time. Sorry for going over time. Questions before we wrap up? And I think let's call it.